When we peer into the world of physics and the cosmos, time becomes even more intriguing, almost like a shape-shifting rhythm that can stretch, shrink, or even stand still depending on the circumstances. In classical physics, think Newton, time was a perfectly regular drumbeat in the background, steady, absolute, and the same everywhere. But in the 20th century, revolutions of relativity and quantum physics absolutely shattered that picture. So let's start with relativity. Albert Einstein's gift to our understanding of time. Einstein showed that space and time are woven together in a four-dimensional fabric called space-time, and that fabric can stretch and ripple. According to this theory of general relativity, time is not an immutable tick-tock. It flows and differentiates at different rates depending on speed and gravity. A clock moving fast, say on a spaceship, will tick slightly slower than relative to a stationary clock, and this is called time dilation due to high velocity. And a clock deep in a gravitational field, say at sea level, ticks slightly slower than one on a very high mountain, because gravity actually warps time. And this is absolutely not just a theory. This is something that they have to measure and account for. GPS satellites, for example, have to correct for these relativistic effects. Their clocks in orbit tick faster than clocks on Earth. That's due to weaker gravity and their motion. And if it's not corrected, the positioning calculations would drift disastrously, off by about 10 kilometers per day of error. Relativity taught us that time can stretch like taffy in the presence of this gravity and high speeds. Time has a flexible tempo. Near black holes, its intense gravity can slow time down dramatically. In theory, at the edge of a black hole, at the event horizon, the time outside the observer nearly stops. This is kind of a cosmic super slow-mo, a far cry from the universal metronome that Newton imagined. Einstein's equations also predicted something even more fantastic: gravitational waves. These are literally ripples in space-time, propagating outward like waves on a pond. When massive objects like black holes or neutron stars collide and merge, they send out vibrations in the fabric of space-time itself. These vibrations make distances oscillate, and since time and space are linked, you can think of time itself as wiggling a bit as the wave passes. In 2015, scientists at LIGO first detected these gravitational waves, hearing a faint chirp from two black holes merging 1.3 billion light years away. It was as if we heard the universe ringing a giant cosmic bell for the first time. While the effect on time for us was minuscule, the stretching compressing of time was on the order of 1 part in 10 to the 21st power, which is unbelievably tiny. It confirmed, however, that time can behave like a wave under certain circumstances. So now, shift from the cosmic scale to the quantum realm, the subatomic world of particles, and we find an even different puzzle. In quantum mechanics, time is treated as an external background parameter. It ticks uniformly while particles and waves evolve. Unlike relativity's malleable time, quantum theory time is more like a fixed beat that everything dances to universally. And this creates a big scientific head-scratcher. Our two best theories, quantum mechanics for the very small and general relativity for the very large, have fundamentally different concepts of time. Reconciling them into a theory of everything has proven challenging, often dubbed the problem of time. Some intriguing new ideas are emerging. One suggestion for quantum physics is that time might not be fundamental at all. It could emerge from something even deeper. In 2024, a group of researchers explored an idea first posed in the 1980s, called the Page and Wouter mechanism. Their study suggested that time could be an illusion woven from quantum entanglement. Entanglement is the ghostly connection between particles that can link their states. The idea here is that if you have a quantum system to act as a clock and it's entangled with another system, the correlations between them can produce what we perceive as time. Time is effectively, in an unentangled, isolated system, nothing changes. Time effectively doesn't exist for it. It's as if the universe is completely frozen. But when entangled with a reference, a sequence of change, or time, emerges. As one physicist in the study put it, the correlation between the clock and the system creates the emergence of time. This is cutting-edge theoretical stuff here. We're basically asking if time itself might be a sort of harmony arising from underlying quantum relations. If true, and that's still a big if, it's poetic, that time might be akin to a beat that materializes only when there's something to keep time with. It's the universal observer. There's also talk of quantum time crystals. Yes, crystals. Time. This sounds sci-fi, but in 2016 and 2017, researchers like Nobel laureate Frank Wilczek's proposed and then observed this time crystal behavior in certain quantum systems. A time crystal is a phase of matter that exhibits a sustained periodic oscillation or motion in its lowest energy state without consuming any energy. Essentially, a system that spontaneously breaks the usual rule that things at a minimum energy are static. It's as if this system has a clock-like oscillation just by its nature. These time crystals oscillate at a fraction of the driving frequency, like hitting a system periodically and it responds at a different period. While not time travel, time crystals show that time-based periodic order can exist similarly to spatial crystal order. It underscores how deeply connected oscillation and time are in physics. Even quantum matter can find a beat to groove to. Our view of time in cosmology also presents grand cycles. One ancient idea revived in modern physics is the cyclic or oscillatory universe, the notion that the universe could go through repeated expansions and contractions, the Big Bang, the Big Crunch, rinse and repeat, while the standard view is an ever-expanding universe from a single Big Bang. Alternatives like Roger Penrose's conformal cyclic cosmology propose that what we think is the end of one universe might seed the beginning of a new one, in a timeless, transcendent way, giving an endless succession of aeons. Other theories imagine multiple Big Bangs or bounce backs. Though these ideas are speculative and debated, they echo an ancient intuition that perhaps time itself on the largest scale isn't linear, it's circular. And finally, relativity introduces a philosophical quandary. If time is just another dimension like space, we can imagine that the entirety of history of the universe laid out in the block universe, where past, present, and future all coexist in four-dimensional structure. Here, the flow of time, or the feeling of now, is an emergent illusion of consciousness rather than a fundamental property of physics. Einstein himself, reflecting on the death of a friend, wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. To a physicist, all moments might be equally real, like all frames of a movie reel exist, even if we perceive them sequentially. It's a mind-bending concept. Time's passage might be a bit like a melody that we hum as we move through the already written score of space-time. And that raises all sorts of questions about determinism and free will, which we'll touch on later. In summary, physics and cosmology reveal a rich, complex portrait of time. It's not a uniform metronome ticking the same for everyone, everywhere. It's more flexible, like an interactive phenomena, capable of stretching in gravitational groove, of entangling into existence and rippling across the cosmos, and perhaps of repeating across eons. Time, in physics, has harmonics in a literal sense, cycles, oscillation, waves, and in a figurative sense, different versions of time for different observers, all part of one grand composition. As we journey onward, keep this strange and scientific perspective in mind. It'll complement the biological, music, and further theoretical views of time's harmonics.